Hello everybody, welcome to our last lecture in Math 142. I know, don't cry, don't cry. I'm trying to hold it together. But for real, what I do want to say is it was an honor being your instructor this quarter. I'm saddened because of our unfortunate circumstances that I was never able to meet any of you face to face. I would say that really the best part of my job is interacting with students. I really can't believe that I get paid to really share what I love to people. I very much enjoy mathematics. I feel like my job is kind of like show and tell, and I get such joy out of helping students understand what is known to be a tough subject. I hope you found my videos useful. I hope you were able to get the help that you needed with the forum and with the live Zoom tutoring sessions. I really did try my best to help prepare you for calculus next quarter. Calculus is such a beautiful subject. I would say calculus out of calculus, the discovery of calculus, I would say, is one of the top 5 discoveries of all time. Not just I guess in terms of mathematics, but of all discoveries humans have made. Without calculus, we wouldn't have engineering. Without engineering, we wouldn't have the technology we have today. So I guess what I want to say is if any of you see me out in public, please feel free or definitely come stop by, say hi. If it allows it, I would love to shake your hand, have a quick conversation, and maybe put some faces to the names that I see on WAMAP. But anyway, before I get too emotional, let's jump in. The last thing we're going to talk about in Math 142 is really an introduction to these things that are called parametric equations. Parametric equations are super cool and super useful, specifically if you're ever going to study physics. Why? The answer is really because what parametric equations do is they describe, or they give us a way to describe possibly the motion of a particle in time. Let me tell you what I mean. Imagine there's a particle and it's moving out in space. So I don't know, it could be a bee moving around, could be a plane doing a loop-de-loop, or it could be an electron in an accelerator. But the whole idea here is when you think about a position, in space, I guess if we're going to be talking about parametric equations just in 2 dimensions, you could easily do this in 3 dimensions. You'll study that in more detail in Calculus 3. But we're going to be talking about particles moving in a plane. So imagine there's some sort of particle that is tracing out some sort of path in two-dimensional space. Now, at a point in time, a particle has a position. It has an x-coordinate and a y-coordinate depending on where you're measuring it, which would be the origin. So if I'm measuring from right here, the particle right here would have some sort of x-coordinate and would have some y-coordinate. But as time goes on, there's really another variable going on here. As time goes on, both the x and y coordinates change. So really, the x coordinate of a particle is a function of time. And the y coordinate of a particle is also a function in time. So at one moment in time, this is your x and y coordinate. At another moment in time, here's your next x and y coordinate. So that is really what a parametric equation is. And we're going to be doing a few examples. So let's say, for example, what we're trying to do is a parametric equation. We're thinking about the position of a particle. A particle has a position x and a position y, but we're going to think about x and y being both functions of time. Both functions of time. Okay, so instead of saying x is a function in time, oftentimes what we'll actually do is we'll say that x is maybe some sort of function of t, and y is some sort of function of t. Let's do an example. Okay, let's go ahead and first graph a parametric equation. Let's erase a little bit of this here. Let's graph the parametric equation. How about x is equal to t plus 3, and how about y being equal to negative t squared plus 3? Okay. To understand this parametric equation, I guess the first thing to note here is notice that x depends on the value of t and y depends on the value of t. X is a function of time and y is a function of time. So if we want to understand what's actually happening, let's go ahead and just make a t-table. This will be kind of the way we kind of brute force or trying to initially understand what's happening. We're just going to plot some points. Okay, so let's see, we have moments in time. So let's say, I don't know, we'll have t, we'll have x, and we'll have y. Okay, so let's look at certain moments in time. So maybe we'll look at time t equals -2, t equals -1, 0, and how about 1, 2, and 3. And we're going to plot these. Make a nice little grid right here. How much space do I need? Okay. Okay, so here is y, and here is x. X is really controlling the horizontal motion of the particle. Y is controlling the vertical motion of a particle. Okay, what's going on, or what would be the position of this particle at time t equals -2? So I guess if you're thinking about the present, that'd be like at time t equals 0. Time t equals -2 is like, or -1, what happened a second ago? What happened 2 seconds ago? What happening a second in the future? 2 seconds in the future? 3 seconds in the future? Okay, well, when t is -2, what will the x value be? We're simply just going to replace t with -2. So x is going to be equal to -2 plus 3, or in this case, x will be 1. Okay, if we plug -2 in for t for y, what are we going to get? We'll get y would be equal to negative. We'll get a -2 squared plus 3. So we'll get a -4 plus 3. Looks like we are going to get out, what, a -1. Okay. Okay, let's just keep doing this. Okay, before we start plotting these points, if we plug in -1 for t, -1 plus 3 is 2. Maybe we'll do all the t's first. If we plug in 0 for t, x will be 3. If we plug in 1 for t, x will be 4. And then we'll get, what, 5 and 6. Okay, what about for y? If we plug in -1, we're going to get a -1 squared plus 3. So -1 squared is 1, so we'll just get -1 plus 3. We're going to get out 2. Okay, what happens if we plug in a 0? Well, we'll get 0 squared times -1. We'll get 0 plus 3. We'll just get out 3. Okay, if we plug in 1, we'll get -1 squared plus 3. We'll get -1 plus 3. Looks like we're going to get out 2. Right, if we plug in 2, we're going to get, that'll be what, -4 plus 3, so we'll get out -1. If we plug in 3 for t, we'll get -9 plus 3. We're going to get out -6. Okay. So we're just going to kind of draw a snapshot of the motion of this particle. At time t equals -2, the particle is at position 1 and -1. So here is 1 and here is -1. This is where the particle is at time t equals -2. At time t equals -1, the particle is now at position 2, 2. So here's 2, and here's 2. Okay. Okay, at time t equals 0, the particle's at 3, 3. So 3, 3. Okay. At time t equals 1, the particle's at 4 and 1. 4 and 1. I'm sorry, is that 4 and 2? Okay, at time t equals 2, the particle's at 5 and -1. And at time t equals 3, we're at 6 and, if we plug in 6 and -6, I'm guessing I made a mistake here. If we plug in 3 squared plus 3, we end up getting -9 plus 6. Okay, no, we're at -6. Okay. I just figured this was kind of like a big jump. So now at time t equals 6, we're way down here at -6. So maybe I put the dot way down here. But what hopefully you're seeing what we're doing is the particle is starting here, and as time goes on, the particle is moving it looks here in some sort of parabolic path. And if we were to let t go negative a little bit more, the particle would be doing this. So it's going to, I guess if we're starting here, or I don't know, start at some spot, some negative time, and as time goes on, the particle will use arrows to describe the path that the particle is taking. So this is what the parametric equation looks like. If x is t plus 3 and y is negative t squared plus 3, this is the path that this particle here is taking. Pretty cool. All right, here's something interesting though. What happens if I just change time a little bit? What happens if we change time a little bit? How about instead of t, what if we replaced t with negative t? So what would that mean if you're just trying to guess? What does it mean? Here I was saying if I replace t with negative t, I'm changing time with negative time. What should that mean? Or what's gonna be different? Okay. Well, so kind of like an interesting question, and I'll show you an animation of all this in just a moment. Question: what if we replace t with negative t? Okay, so let's just do some adjustments. So instead of having t here, now we would have a negative t. Now we would have a negative t. Okay. Over here, we would replace t with negative t. So now we'd have a negative t squared. But you could also think that since I'm squaring this, negative t squared will be the same thing as just t squared. So this is equivalent to still just negative t squared plus 3. Let's see how this changes the motion of the particle. Okay, same exercise. We're just going to plug in values of t and see what happens. Okay, if we plug in negative 2, now we're going to get negative 2 plus 3, or that'll be 4 plus 3. It looks like we're going to get 7. Oh, I'm sorry. Negative, this is 2. We'll get 2 plus 3. This is 5. Okay, if we plug in negative 2 over here, we'll get a negative 2 squared plus 3. This will be 4, negative 4 plus 3, we'll get negative 1. Okay, if we plug in negative 1 for t, we're going to get 1 plus 3, so we'll get out 4. Maybe we'll do it all for t first. If we plug in 0, we would get 3. If we plug in 1, we'll get negative 1 plus 3, we'll get out 2. Hopefully we can kind of see the pattern here. 5, 4, 3, 2, we should get 1 and then 0. Okay, over here, if we plug in negative 1, what are we going to get? We're going to get, negative 1 plus 3. Negative 1 plus 3, we're going to get out 2. If we plug in 0, we're going to get out 3. If we plug in 1, we'll get negative 1 plus 3, we're going to get out 2. Okay, if we plug in 2, we'll get what? Negative 4 plus 3, so we'll get out negative 1. And if we plug in 3, we'll get negative 9 plus 3, we'll get out negative 6. Okay, so now what's going on? Okay, how has this changed? Okay, well at time t equals negative 2, now we're at the spot 5, negative 1. Now we're here. Okay, a second, or I don't know, it depends on the units of time, maybe a second later, now we're at 4, 2. Okay, a second later, now we're at 3, 3. Okay, now another second, now we're at 2, 2. And then we're at 1, negative 1. And then we would be at time t equals 3, we would be at 0. We'd be at 0 and negative 6. But the key thing to realize here is we started here, and as time went forward, now we're going this way. Now, compared to the last graph, this is the same path. This is the same path that the particle was taking, except now, when I replaced t with negative t, I kind of just reversed time. The particle's now just traveling along this path in the opposite direction. Pretty cool. So, if I have just a t there, it follows its normal path. If we replace t with negative t, you're still getting the same curve, or the same path, as you're just traveling in a different direction. Here's an interesting question. What if we replaced t with 2t? What do you think is going to happen here? Do you think we're going to get a different path? we won't get a different path. I'll show you this animation in Desmos in a moment. This is just going to make you travel along the path or the curve twice as fast. If we replaced t with 5t, it would be the same curve. You'd just be traveling along it at a pace of 5 times faster. You could even replace t with something crazy like, I don't know, an exponential function, like e to the t. This means, if you remember how an exponential function works, exponential functions start out small and they get big really quick. This would be this, you'd be traveling along the same path, except you would first be traveling along it a little kind of slow, and then you would be increasingly fast as you went on. Let's see some animations. We'll see you in Desmos. Okay, here we are in Desmos. Desmos is such a great place to experiment with parametric equations. I highly recommend that when you're doing your homework to return to Desmos and really get a feel for what's going on. Okay, so what's a great way to plot parametric equations? Let me show you how to use Desmos to do this. So what we want is we want a function to control x and we want a function to control y. So what I'll write is f of t. So whatever I put here, this will control my x coordinate. So for the example we just did on the board, x of t was what? It was t plus 3. Okay, we're not going to view this. This is what the x coordinate is doing as time. Okay, but let's now have g. Let's have g control the y coordinate. So how about a negative t squared plus 3? Okay. Okay, but what we want to do here is I want to have this be the x coordinate and this be the y coordinate. In Desmos, I think we can just make an ordered pair. So here's an ordered pair, or just, I don't know, I guess you could open 2 sets of parentheses. So let's do f of t, and let's do g of t. Okay, so right now, it's plotting all of these sets of points. It's plugging in from t equals 0 to 1, and it's plotting all those points here. What's better to do is just to have this animated. And what did we have on the board? We were doing it from what, -2 to -3, or -2 to 3. So we could put -2 to 3, so you can see that portion of the graph, and so on and so forth. But to make this kind of be fun is let's start at -2 and let's have it trace out to an arbitrary number. We'll make it a slider. So we'll go from -2 to n. Desmos is going to ask if I want that to be a slider. Yeah, we want it to be a slider. And in this case, it looks like I'm starting at -2, so let's have n start at -2, and I don't know, let's let n go to, now let's see what it does if let's let it go to 100. I don't know if it's going to trace this out pretty quickly. Okay. Okay, so if I hit play, okay, let's go over here and slow this down. Okay. So if you click right here, you can slow down the speed, and let's have it only go in the forward direction. Okay. So if I hit play here, we can see the motion of the particle as time goes on. Let's even slow this down. Let's have it trace it out a little slower. Okay, here we go. Okay, and let's zoom out maybe a little bit. Okay, so if I hit play, we can see what's happening is it's plotting these points. It's plotting the motion of this particle as time goes on. So it's plotting it from time t equals -2 to t equals n. Pretty cool, pretty cool. Okay, well, notice what happens when we replaced t with -t. So instead of replacing the t's here, I think I can just go right here and put a -t and a negative. Okay, let's see what happens now if I hit play. Notice here that now we're just traveling in the opposite direction. When I replace t with -t, it's the same curve, it's just going in the other direction. Now you might be wondering what's happening over here. It's because Desmos is plotting this from -2 to n. I mean, we could, if I say this is -10 to 10, it'll start further back, and I guess you'd want your n to go back further. Maybe we can do that. Maybe I can zoom out a little bit. Well, oh, there we go. Okay, so if we hit play, we can see the motion that this particle here is taking. Pretty cool. Awesome. And again, if I go back, I just want it to now go forward. In this case here, same path, just traveling in the opposite direction. Okay, let's do something else a little bit more fun. Instead of placing t with negative t, let's replace it with 2t. Let's see if it goes a little faster. Here it comes. So now it's plotting more because it's starting at t equals negative 10, so it's plugging in negative 20. But hopefully we can see here, if I hit play, it's traveling quicker. Let's even go back a little bit further. Let's actually have it start from 0. That'll make it hopefully a little bit more clear. Okay. And we'll plot from 0 to n. Let's hit play. Or let's go from, 0 is fine. Okay, so now it's just going to start, in this case, right at the, on the board at time t equals 0, we are at 3,3. So we're imagining the particle starting at the point 3,3. So if we hit play, okay, that's just normal time. We can speed up time. Let's put in like, I don't know, we did 2. Going faster. Let's plug in like 5. Just same path, just traveling faster. We can plug in like 10. And this thing should be zooming. Pretty cool. All right, so that's what's really cool about parametric equations is we can talk about the path that a particle takes, and by changing the t, it doesn't change the path the particle takes, it just changes how the particle, I guess, traverses the curve. Let's think about another parametric equation that we've kind of secretly already been using this whole quarter. How about the unit circle? So let's have our x-coordinate be controlled with cosine of t, and let's have our y-coordinate be controlled with sine of t. Okay, and let's do f of t and g of t. Okay, and let's have it go from 0 to, I guess we could just do, let's see, I guess we could go to 10 pi if we'd like. Okay, let's zoom in. Or, not just 0, let's have the endpoint be a slider. Let's put n. Okay, let's zoom in a little bit. And let's start at time, n at 0, and I don't know, we could let n go to, I don't know, I guess we could let n go to 10 pi. Okay, let's hit play. Let's see what happens. Let's also, I also want Desmos to kind of plot the point, maybe to see a little bit better. Let's plot f of n and g of n. So this will just plot a single point as it's moving around, rather than t will trace out all the points. It'll kind of leave the path as the particle moves. If I just put n here, it'll just have that single point. So notice when I hit play, you can kind of see what that point is doing as we're traveling around the circle. When x is controlled with cosine, okay, let's have this go only forward. So when x is controlled with cosine and y is controlled with sine, we have a circle. We have a particle that's just moving around this circle. Pretty cool, pretty cool. Okay, and again, if we replace t with negative t, now we should just be moving not counterclockwise but clockwise. That's just kind of like almost that idea of a negative angle. So now we're just, oh well, now I should put a negative here for the n. So notice now it's just traveling in the opposite direction. Pretty cool. Okay, let's do something cool. Instead of speeding time up, speeding it down, really this particle has a constant speed. Let's do something cool. Let's change time. Let's make it e to the t. E to the t. Let's have this almost like a race car traveling around this curve, except now its speed's going to start out slow and it's going to be getting really fast as it moves around. So what if we replace t with e to the t? So now I'm going to replace this with e to the n and e to the n. Okay. Okay, so right now when t is 0, when t is 0, notice e to the 0 would be 1 and e to the 0 would be 1. So now it's just starting at a different point. So it's starting here rather than the point 0, 1. So let's go ahead and hit play. And yeah, let's just hit play, see what happens. That went pretty crazy. Let's slow down how fast it sweeps out n. Okay. And let's maybe let n. Let's have this go back a little bit. Let's go back to, I don't know, let's do -10. Let's go from -10 to n. Let's have n start at -10. Okay, let's see what this does. Okay, so let's hit play. So notice it's going a little bit. I guess it's really slow, but if we zoom in, this thing is traveling really slow. And if, I guess, while this is going on here for a second, oh, notice it's starting to move. I'm going to push pause here for a second. But look at the graph of e to the x. E to the x. This particle should start out moving slow, and then its particle's going to speed up really quickly. Let's get rid of that. Okay, zoom in. So notice it was traveling like a snail at first. Let's hit play. So now it should start speeding up. So now it's going faster, but still traveling that unit circle. Still traveling that unit circle. But now it's just going to start going super duper 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 fast. Whoa, are you dizzy? I am. Oh my goodness. Yeah, this is like, you know, when you're a kid, you want that guy at the carnival to turn the speed up on the ride, and then you're like, slow it down, slow it down. All right, all right, let's push pause. But this is super cool. What's actually really cool is we could also let's go back and make this a t again. Let's say we wanted to not travel a circular path, but an elliptical path. Okay, what would we do there? Let's have n start back at 0. Okay. Let's see. Oh, let's have this go from 0 to n. Okay. Oh, I want this to be an n. That's what's going on. Okay, there we go. All right. So we're traveling along. Okay, so let's say I want it to be not a circular path, but like an elliptical path. Well, what I basically want to do is just change the amplitude of x and y. So the amplitude of cosine, this is saying that the x-coordinate, as time goes on, is really only going to be varying between -1 and 1. So that's why the x-coordinate only goes from -1 to 1. Or similarly with sine, the y-coordinate only goes from -1 to 1. But if I want to have this stretched out a little bit more, what if we change the amplitude of cosine? So let's go back. Okay, what if I want the x value to vary between -3 and 3? Well, if I put a 3 here now, I'm changing the amplitude. So now I should get an ellipse. Okay, the x-coordinate is going to be going between -3 and 3, and the y-coordinate is going to be going between -1 and 1. So if we go back and I hit play, let's speed this up now just a little bit. Notice here, now it's traveling along an ellipse here instead. Okay, if I could change how far the x-coordinate goes out, do a whole bunch of really cool things. We could even change the period. So what if I change this to 2? Okay, well, this is now so what's going on here? What's going on here? Let's kind of pause here for a second. What's going on? Okay, well, the x-coordinate, let's see, the x-coordinate is going between -1 and, well, the x-coordinate and y-coordinate are still going between -1 and 1, but it looks like as it's not completing its full circle. I guess it has to do with the period difference here. Let's see what's going on as time is going on. Okay, so let's go back up. So as time is going on, initially the x-coordinate is getting bigger, or the x-coordinate, oh, the x-control is coordinate with red. So the x-coordinate is starting to get smaller. It's starting to get smaller, and it's going to get to -1. It's going to get to -1, I don't know, where is this point? At time t equals pi over 2, but for the y-coordinate, at this point, it'll be at 1. So once we get to pi over 2, it'll be 1. But now the x-coordinate is going to start getting bigger again. It's it's going to start getting bigger again. So as time went on, once we got to here, roughly pi over 2, that's when we're roughly right here, the x coordinate is -1, the y coordinate is 1, but now as time goes on, now the x coordinate is going to start getting bigger again, so that's why it's actually going backwards this way and the y coordinate is going down. So that's why it's kind of bouncing back and forth between these two spots. But you could get other cool shapes by, I don't know, we could do 3. Well, look at this crazy path this particle could take. So this is a, I don't know, super cool, I don't know, go-kart course or something. So changing the periods or sines and cosines can be really fun. Really fun with parametric equations. Really super cool. Okay, so I highly recommend play around with Desmos and these parametric equations. It's super fun, and hopefully it gives you a better understanding of really what they're doing. Okay, let's go to the board and do some more examples by hand. We'll see you there. Pretty cool, huh? I love parametric equations. I don't know. We have now a great way that you can describe the motion of a particle. This is used all the time in physics, all the time in calculus. All right, so let's kind of think, well, what if we didn't have something cool like Desmos to draw these parametric equations? What kind of techniques could we use to be able to sketch these, again, without having to plot a bunch of points? Well, there's this technique that we could use that's called eliminating the parameter. So let's do it on this example here. So let's get away from t-tables. But that's how you really do anything in math when you're first learning something. I mean, you don't really have all your super cool techniques. I mean, you kind of just brute force something, and I don't know what to do. Let's just kind of probe it, you know, what happens with this t-table, and then you get a better feel for what's going on. You kind of get your feet planted, and you can start doing a lot more cool things, or get to results a little bit quicker. So what do we have here? We had negative t squared plus 3. Okay, so how could we have got to this graph quicker? There's a technique that's called eliminating the parameter. Eliminating the parameter. Okay, I don't even know if I spelled eliminating right. I spelled eliminating right? I don't know. My notes say there's one L, but I don't know. I didn't major in math. Eliminating the parameter. You could laugh at me, but yeah, I'm a terrible speller. Okay, so what we're going to do here is when you want to eliminate the parameter, you just kind of want to get rid of t. You want to try to get this to look like y as a function of x or x as a function of y. So notice for specifically when we were graphing that last example, we just saw the x coordinate and the y coordinate. There was no t anywhere. T is how the picture is getting animated. You don't see it. Just like you don't see time, you see things, you see x and y coordinates of things moving in space, but you don't see time. Time is the idea that things are moving or changing position. So let's kind of eliminate time to just see position. So what you'll do is you're just going to solve one of the equations for t, and it's as simple as plugging it into the other one. Okay, let's solve for t. I think this is going to be the easier one here. So solving for t, we're going to get that t is going to be equal to x minus 3. And then we are going to replace t, we're going to move t into the y. So what we're going to get is that y is going to be equal to a negative. We get an x minus 3 squared plus 3. Okay. Well, if you are pretty fresh at, I don't know if you remember a lot of the stuff from Math 141 or Pre-Calculus 1, you might say, hey, this looks a lot like the vertex form of a parabola. The vertex is at 3, 3, and it's frowny face. That's exactly what we saw. It's exactly what we saw. The vertex would be at 3, and 3, and it would be a frowny face parabola. Okay, what would be the y-intercept? Well, what would be the y-intercept? Well, what if x is 0? Well, if x is 0, we would get negative 3 squared plus 3. We would get, what is that? Negative 9 plus 3. What is going to be negative 6? So, negative 6. So, and that's exactly the That's exactly the curve that we saw. Now, how the particle traverses the curve depends on what you're doing with t here. But even if this was 2t, even if we replaced t with 2t, and we put a 2t here, okay, maybe if you could solve, if you solve for t here, the only difference is now this would be divided by 2. Okay, if I plugged it in over here, this would be divided by 2, and it would be times 2. It would be times 2. The 2's would cancel out, and you would still be left with x minus 3. It's the same. It's the same path. It's the same path. Even if t was e to the t, even if this was e to the t, and this was e to the t. Well, you could, instead of solving for t, I guess you could have solved for e to the t. So you'd have that e to the t would be equal to x minus 3, and you'd replace e to the t with x minus 3 right here. And you're still have that same path. It's just now we're traversing the path differently. It's like this is controlling the speed. Our speed is exponential. Okay. So you could also expand this. I'm not sure if WAMAP is going to want you to expand these or not. But let's just kind of go back to what we originally had. We had x plus 3, and this was negative x squared plus 3. So we had, this was a t. Sorry, this was a t, and this was a t. So we had what t was x minus 3. So y would be negative. We'd have x minus 3 squared plus 3. We could expand this if you'd like. So x minus 3 squared, if you FOILed that out, you'd get x squared minus 6x plus 9. The O and the I in FOIL is what's giving me that negative 6x. Plus the 3, you could distribute in that minus sign. You'll get negative x squared. Now plus 6x minus 9 plus 3. So we'll get negative x squared plus 6x. Looks like minus 6. So here we have a parabola. The negative in front of x squared is saying it's that frowny face parabola. Pretty cool. Okay. So this is what they call eliminating the parameter, a way to sketch the path of the particle without having to plot points. But what you're also going to want to always add, to these pictures is an arrow indicating how the particle is traveling along the curve, where t is going from negative infinity to infinity, or they might say with increasing t. As time increases, what direction is the particle going? Well, instead of, again, plotting points, what you could do is we would already realize with eliminating the parameter, we'd have a curve like this. Now, to figure out how it's traversing the curve, you can plot these. So this is x on the y-axis and t. Well, what is this? This, if I'm plotting x as a function of time, is t plus 3. That's a line with a y-intercept of 3 and a slope of 1. Okay, so this is just saying that as time increases, the x-coordinate is getting bigger. Okay, over here, if we plot y, it's a negative t squared plus 3. That's a frowny face parabola shifted up 3 units. Okay, so what this is saying is as time is increasing, what are the y-coordinates doing? Well, initially the y-coordinates are getting bigger, and then the y-coordinates are going to start to get smaller. So let's say if we start at time t equals 0, so we would be right here. We want to know as time goes on, am I going this way along the curve, or am I going this way along the curve, or am I going this way along the curve? Well, as time goes on, x is increasing, so x is going this way, and initially y is going to be getting bigger, and that's exactly what we see right here. X is getting bigger, and initially y is getting bigger. And then as we go a little bit, x is still getting bigger, but now y is decreasing. So that's why we are traveling along the curve in this direction here. Remember when we replaced t with negative t? Remember when we replaced t with negative t? We'll be doing more examples than just this one. Hopefully I'm not confusing you too much. Okay. When we replace t with negative t, so we had negative t. When we replaced t with negative t here, and we were squaring it, negative t squared is the same thing as t squared. So replacing t with negative t does not affect this graph, which should make sense because this is an even function, so it's symmetric about the y-axis. However, x equals negative t plus 3, if we were to plot this, here's x, here's time, we have a y-coordinate of 3, now we have a slope of negative 1. So now what's happening? Well, as time increases, the x-coordinate is getting smaller, or the x-coordinate starts positive, or I guess positive as time goes on, it's getting less positive, and all of a sudden the x-coordinate is going to start getting negative. Okay, so what's happening here? Well, as time goes on, the x-coordinate is some positive number, and then as time goes on, the x-coordinate is going to be getting negative. And it's going to be, like, it's getting closer to 0 and then negative. So in this case, we'd be traveling along the curve in this direction. And again, you can see that the y-coordinate starts out negative, and the y-coordinate starts negative, and as time goes on, it's going to keep getting, the y-coordinate is negative, and as time goes on, it's going to be becoming less negative, and then the y-coordinate is going to be positive, and then the y-coordinate is going to then start to get smaller. Let's do some more examples. Let's say we have the parametric equation. How about x equals the square root of t and y equals 9 minus t. What I often find useful when plotting parametric equations is actually to to plot or roughly plot x as a function of time, then y as a function of time, and then try to think about what values x can be and what values y can be. So, for example, let's plot x on the, I guess what we traditionally call the y-axis, and let's plot t on traditionally what we call the x-axis. So x being equal to the square root of t, hopefully remember what the square root of t looks like. Square root of t kind of looks like, maybe like a chicken wing or something like that. I don't have a better name for this shape. Oh, maybe like not quite like a Nike sign, but maybe. Okay, so this is what the x-coordinate is going to be doing as time goes on. As time goes on, the x-coordinate is going to be increasing, okay? And y is a function of time. So almost right off the bat, I should pause here for a second. Notice here that there is actually a restriction on t. We can't plug any negative values in for t. So we should take a note immediately in this problem that t has to be greater than or equal to 0. If you plugged in a negative value of t, you'll get no output for x. So now, if we want to plot y as a function of time, okay, so y, and here is t. Well, this is a line. If you don't like the way this looks, you could think about plus the opposite. You could think about this as 9 plus a negative t, which is the same thing as negative t plus 9. This is a negative t plus 9. This is a line, has a y-intercept of 9, and has a slope of negative 1. So it's going to look like this. Now, you may be tempted to draw the entire line, but remember, from here, we realize that t has to be positive. So I'm not going to plot anything to the left over here. Y is equal to 9 minus t, but I have the restriction here that t is greater than or equal to 0 from what our x is as a function of time. So, all right. So from these graphs, we can think about what values x can take on. Okay, well, t has to be greater than 0, but let's notice that x can only be between, well, it looks like x is going to be between 0, and x can go from 0 to infinity. All right, over here, looking at our y's, our y values can go from 9, that's the biggest y value we can get, and y, I guess the smallest could be negative infinity. So y can be from negative infinity to 9. And we're just going to hold on to these. That could be equal to 9. Okay. Okay, but what we want to plot is we want to plot this parametric equation. So all we've done here is plot x as a function of time and y as a function of time. I want to plot x and y, and I want to see what the path this particle would be taking. So let's eliminate the parameter. Okay, there's a couple ways we could do this. It doesn't matter where you want to solve for t. I think in this case, maybe it'd be easier for us to think about solving solving t in terms of x. So if we square both sides, that would be saying that t is equal to x squared. And if we plug t in here for y, we're going to get that y is going to be equal to 9 minus x squared. So let's go ahead and plot the path that this particle is going to take. All right, 9 minus x squared. This is a frowning face parabola shifted up 9 units. Okay, it has x-intercepts at 3 and negative 3. If you factor this, it factors to 3 minus x times 3 plus x. So it has x-intercepts at negative 3 and 3. Now, if you didn't do this exercise here from the beginning, you might be tempted to say that this is the path the particle is taking. Okay, and I don't know, maybe you would plug in t equals 0 and say, well, you know, when t is 0, you would say, well, then what? X would be 0, and then y would be 9, and then maybe a moment later you'd say, oh, well, what happens at time t equals 1? If you plug in 1, the square root of 1 is 1. 9 minus 1 is 8. So you would say, at time t equals 0, we're here, and then in a moment later, we're here. So you might be saying that the particle is traveling in this direction. Okay, but the problem is this is not the entire path. We have to be careful with knowing what x can be and what y can be. Okay, so really, we have this graph, but it's only going to live in the window from x from 0 to infinity. So this left portion of the graph will not be there. T has to be greater than or equal to 0, and when time t equals 0, we're at the point 0, 9. Okay, and y values, the y values can go from negative infinity up to 9. So this is actually the path the particle takes. Okay, and what's happening? Are we starting here? I know I already plugged in t equals 0, but you want to ask yourself the question, are we starting here and then going forward, or are we somehow starting over here and going backwards? Well, we should notice here that as time goes on, x is getting bigger. So as time goes on, as time goes on, you don't see time here. This is x, and this is y. As time goes on, the x-coordinate is getting bigger. As time goes on, the y-coordinate is getting smaller. So we must be traveling in this direction here. Awesome. Let's do another example. So whenever you plot a parametric equation, you want to plot the path, and then you want to use an arrow to indicate the direction of increasing t, which is what we've done here. Let's say that we have that x is equal to t squared, and then that y is equal to t to the 4th plus 1. Okay. We want to plot this parametric equation. The first thing I'm going to do before eliminating the parameter is I'm going to think about the values that x can take on and the values that y can take on. Okay, first of all, notice that t could really be anything here. There's no domain restriction on t. You could plug in negative values of t here and positive values of t here. You could plug in negative and positive values of t here. Okay, so I don't have any restriction on t. Really, I'll write that over here. T, in this case, can go from negative infinity to infinity. Okay, let's plot x as a function of time. Here's x, here's t. Okay, this is just the graph x equals t squared. So that's just going to be a parabola. So this is x equals t squared. Okay, over here, this is y equals t to the 4th plus 1. T to the 4th, or if you want to think about x to the 4th, t squared, t to the 4th, those are still going to look like parabolas. So t to the 4th plus 1, it's going to be kind of a skinnier parabola, but it's going to be shifted up 1 unit. So it's going to look something like this. So here's y, and here's t. Okay, so t can go from negative infinity to infinity, but what values can x possibly be? Well, the smallest x can possibly be is 0, and the biggest x could possibly be is infinity. Over here, the smallest value y can be is 1, and the biggest y can be is infinity. Okay, so when we're plotting our parametric equation, this is the window that the path is going to live in. Okay, now there's a couple different ways we can eliminate the parameter. Okay, let me give you a couple different options here. I guess you could go ahead and you could solve for t here. So maybe you say that you take the square root of both sides. So you'd say that t, I guess t could be the plus or minus the square root of x. Okay, it actually, t could be the plus or minus square root of x. Okay, and if we were to plug that in over here, you would get that y would be equal to plus or minus the square root of x to the 4th plus 1. Whether the number is positive or negative, when you take the 4th root, or when you take it to the 4th power, it's going to be positive. A negative number to an even power is positive. So this is the same thing as just the square root of x to the 4th plus 1. Okay, what's the square root of x to the 4th power? Well, let's think about that. Well, you could brute force it by saying that's the same thing as the square root of x times the square root of x times the square root of x times the square root of x. That's what the square root of x to the 4th means. But the square root of x times the square root of x, well, that just gives you an x. And the square root of x times the square root of x, that just gives you another x. And x times x is x squared. So this will be x squared plus 1. Okay. Another way to think about that is you could think about exponent rules. Remember, the square root means the same thing as x to the 1/2 power. So when we see the square root of x, think about that as x to the 1/2 power, and we're raising that to the 4th. Well, our exponent rule says that we can multiply these. So this would be the same thing as x to the 1/2 times 4, and 1/2 times 4 is 2. So we'd still get x squared there. Okay, that's a nice way to do it. Okay, we would still get back to x squared plus 1. Okay, here's even another way you could have done this. Sometimes you have to be a little bit creative when you're eliminating the parameters. Okay, notice here that y, t to the 4th is the same thing as t squared squared plus 1. But t squared is equivalent to x, so I can replace t squared with x. So I think there's like 3 different ways we could have thought about this. But we'll still get x squared plus 1. Okay. Kind of fun. I always love seeing different ways to use math to get to the same place. Makes me feel good that math works. All right, so regardless, we got that y was equal to x squared plus 1. We got y is equal to x squared plus 1. So what does that graph look like? Okay, so here's 1. Now we're plotting y and x. So that's a happy face parabola shifted up 1 unit. Okay, but is it going to be this entire graph right here? No. I have to remember I only want the window from x going from 0 to infinity and y going from 1 to infinity. So I just want the picture from 0 to infinity on the horizontal axis, and nice here from 1 to infinity on the y-axis. So this is going to be the path that the particle is taking. Okay, but now let's think about what's happening. Okay, what is this particle doing? Okay, well, if t is negative, we have some sort of negative t value, well, the x-coordinate's going to be pretty big. So I'm thinking about over here. So a negative t value. Okay, well, x is going to start out positive, and as time goes on, it's going to start out positive, but the x-coordinate is going to be decreasing to 0. And similarly over here, the y-coordinate, I'm thinking about some negative t here. The y-coordinate will be positive, and as time goes on, the y-coordinate will be decreasing. So initially, the point, if you plug in, I don't know, like for example, if you plugged in t equals I don't know, how about just -1 for, all right, let's plug in -2. Okay, well then x would be -2 squared, so x would be 4, and y would be -2 to the 4th, that is 16 plus 1y would be 17, so at time t equals -2, we're at like 4 and 17, we'd be right here. Now as time goes on, the x-coordinate decreases and the y-coordinate decreases. Okay, so we must be first traveling over here, but then at time t equals 0, the x-coordinate is 0 and the y-coordinate would be 1, not a surprise. But now for positive values, so now if t is positive, what's going to be happening? Okay, as time goes on, well, the x-coordinate's now going to be increasing, and now the y-coordinate is going to be increasing. So now it's going to, I guess we're at negative time, it's going to be somewhere over here. When we're going from negative time to 0, this is where we'll be at time t equals 0, and then now as time goes on, we're actually going to go back. So now we're actually going to be going back this way. So if we're at, I don't know, time t equals -10, we'd be somewhere over here. As time goes on, we'd be traveling along the curve this way, and when we get to time t equals 0, we would be right at the vertex, I guess, of this parabola, and as time goes positive, we'll go back this way. So we're going to kind of use two sets of arrows to say that the particle first starts over here, comes down, and then it's going to bounce off and go back. Okay. I'll show you some animations in Desmos of this in just a moment. But let's do one more example before we go back to Desmos. Okay, let's say for the next example, we have that x is equal to e to the -t, and we have that y is equal to e to the t. Okay? So before I do anything here, what I'm going to do is I'm going to think about the values that x and y can take on. Y is equal to e to the t. Let's start with that one. I hope we're all familiar with the graph of e to the t. It's an exponential function. Exponential functions have asymptotes along the x-axis. So e to the t looks like this. So this is t, and this is y. So we should notice here that what values can y be? Okay, well, y can go from, it looks like from 0, well, not exactly but 0, but from 0 to infinity. So y can go from 0 to infinity. Okay, well, what does e to the -t look like? What does e to the -t look like? Well, if we're thinking about function transformations, here I have e to the t. What's e to the -t going to do? What happens when you replace your, I guess, your input variable from a t to a negative? That's just going to reflect you across your horizontal axis. I guess your t values were positive, and now your t values are negative. It's going to reflect over the vertical axis. So e to the -t is actually exponential decay. I think of this as exponential decay. So here's x and here's t. This would be exponential growth. So also we should note that x can vary from 0 to infinity also. So noticing here when we're drawing the path that this particle takes, the path is going to live actually in the first quadrant of the xy grid. Okay. So, and also notice that there's no restriction on t. T, you could plug in any value of t in here you'd like. Okay, let's try to eliminate the parameter, and I think there's a couple ways you could do it. Okay, the way I'm going to do it is, well, I guess if you want, you could solve for t. Maybe you go here and you want to solve for t. So you'd have that x would be equal to e to the -t. I want to solve for t, so I need to use the inverse function of an exponential, which is a natural log. Okay, so this will be the same thing as the natural log of x will be equal to -t. Okay, you can multiply both sides by a negative. So we're going to have that t is going to be equal to negative natural log of x. And if you wanted to, we could plug that back in over here. I would say this isn't going to be the cleanest way to do this problem, but this is one approach you could take. So y would be equal to e to the negative natural log of x. I guess there's a couple ways you could think about this here. One thing you could think about is, what does a negative exponent really mean? Remember that x to the negative n really means 1 over x to the n. Or how about when you think about something like x cubed, this kind of means multiply by x by itself 3 times. But if you think about x to the negative 3, this is equivalent to 1 over x cubed. So I like to think about negative exponents as not multiplying by x 3 times, but this would be like dividing by x 3 times. Negative exponents to me are like repeated division rather than repeated multiplication. So using this exponent rule, this is equivalent to 1 over e to the natural log of x. E and natural log, those are inverse functions. They cancel each other out. It's just like squaring and square rooting. If you have an exponential e and natural log, those are inverse functions. They undo one another. This is just 1 over x. Okay, I guess another way you could have thought about this, is this is the same thing as e instead of e to the negative natural log of x. This is the same thing as e to the negative 1 times the natural log of x. And I guess you could have said, oh, well, this is the same thing as e to the natural log of x all to the negative first power, using that exponent rule that x to the n to the m is the same as x to the n times m. Kind of just doing it in this direction. So you could say, oh, this is the same thing as 1 over e to the natural log of x, which is still the same thing as 1 over x. Okay, so when we eliminate the parameter, however you want to think about it, we're going to get y equals 1 over x. We're going to get that y is equal to 1 over x. And maybe just as another tip, maybe you didn't like working with natural logs. Well, notice here for a second, x being equal to e to the negative t, that's equivalent to 1 over e to the t. But e to the t is the same thing as y. So x would be equal to 1 over y. And if you want to think about this as maybe x over 1 is equal to y over 1, you could reciprocate both sides, which just says that 1 over x is equal to y over 1, or we still get that y would be equal to 1 over x. So if you didn't want to work with natural logs, you could have tried to make an e to the t show up somewhere, so you didn't have to use a natural log. Okay, but either way, we get 1 over x. Okay. What does the graph of 1 over x look like? I hope you're kind of familiar with the the 1 over x function. So here's y and here's x. It's one of our toolkit functions. So y equals 1 over x looks like this. But is this the path that the particle is going to be taking? No, remember, we only have the window from x going from 0 to infinity and y going from 0 to infinity, so we only want the portion of the graph that's in the first quadrant. So we wouldn't have this portion of it. Okay. So this is the graph we get when we eliminate the parameter. Now what we want to know is the particle traveling this way along the curve, or is it traveling this way along the curve? These graphs will hopefully help us. Notice here that as we move on, what is the x-coordinate doing? The x-coordinate is decreasing. The x-coordinate starts out positive, x is decreasing, but y is increasing. So as time goes on, the x-coordinate starts out positive, and then it's getting closer to 0. The y-coordinate, as time goes on, the y-coordinate starts pretty small, and then the y-coordinate is getting bigger. So the particle must be traveling in this direction. As time goes on, the x-coordinate is getting closer to 0, and the y-coordinate is getting closer to infinity. So this is the direction the particle will be traveling. Okay, let's just take a look at these in Desmos just to show you, I guess, or to just check our answers. We'll see you there. Okay, let's take a look at those examples of the parametric equations we did by hand. So I think the very first example we did, we had our x component was controlled with the square root of t, and our y component was controlled with 9 minus t. Okay, and if we plot x as a function of time, there we have that square root function. If we plot y as a function of time, we had that line. We had the line. Okay, notice here that we have a variable restriction. T does have to be bigger than 0 to get out a meaningful x input. Okay, and when we eliminated the parameter, what did we get? When we eliminated the parameter, I think we got y equals 9 minus x squared. We got this graph right here, but we realized it couldn't be this entire graph. It could only be the right-hand portion. Okay, so let's plot it. So here I have the x component. Here I have the y component from 0 to n. If we hit play, let's go back. I want to plot this here. So as time goes on, we can see it's not this entire portion, it's only this portion right here. And I mean, just to verify, I know I am starting n at 0, and I have it plotting from 0 to n, but even if I plug a negative value here, like -10 to n, and let n go from -10 to, I know I'm going to 10 pi here, it doesn't really matter, we'll leave it at 10 pi, sure. Oh, -10. Okay. Notice here when I go over here, it's giving me an error. It's giving me an error. It can't plot anything. It's not plotting anything. It doesn't make sense. It doesn't make sense for the t value. Notice here t is going from -10 to n. So I'm plotting. So here I'd be plotting t from -10 to -6, but I'm not getting any outputs because it doesn't make sense for us to have a negative t for this example. We're only getting portions of the graph. Only getting portions of the graph when t starts to be positive. So we're only getting the right portion of that parabola. And there we have it. Pretty cool. Okay, what other one did we see? The other one we saw, we had x was t squared. So setup I kind of have here is nice because I can just kind of replace my f's and g's here, and then everything else here is taken care of. So x was controlled with t squared, and y was controlled with, I think, t to the 4th plus 1. Okay. Okay, so in this case, okay, that's x as a function of time, and then here's y as a function of time. Those are the graphs we drew up on the board. Okay, now what's going to happen? In this case, t, notice here, it makes sense for negative time. I get outputs for x's and y's for negative time. So there was no restriction on t here. So let's go from -10, and we'll let time go on. And when we eliminated the parameter for this one, I think we got what? It was x squared plus 1. X squared plus 1, let's get rid of these. Okay, but I think we realized it wasn't going to be this entire graph here because notice the x-coordinates can only be positive, can go from 0 to infinity, and the y-coordinates can go from zoom in here, from 1 to infinity. So we didn't get the entire portion of this graph, we only got the right-hand spot. And let's make sure that that's what it's doing. Okay, so let's plot this, and we're starting at negative t. And I think for this one, remember, this is plotting the whole thing. We don't have the left-hand portion. I think we started over here, we came down and bounced and came back. So let's verify that that's actually what's happening. So let's just go ahead and hit play, and let's speed this up a little bit. And let's see what that does. Okay, let's hit play. So notice this is exactly what's happening. You see that? So the particle's coming down, it bounces, and then it goes back. Pretty cool. Pretty cool. All right, and then we did, what's the next one we did? We did x was e to the negative t, and we had y was e to the t. E to the t. Okay, let's have n start at 0 for right now. Let's have it go way back over here. Okay, so I think when we eliminated the parameter on this one, we got y equals 1 over x. So that's what the graph of 1 over x looks like, one of our toolkit functions. Okay, but if we look at our x coordinates, well, our x values can only go from 0 to infinity, and also our y values can only go from 0 to infinity. So we shouldn't have this entire graph here. We should only have this right-hand portion. And let's see if that's exactly what's happening. So as time goes on, let's hit play. And I think from the board, I think we saw that the particle starts over here and it goes this way along the curve. So let's hit play. Let's see. Zoom in a little bit. Yeah, that's exactly what's happening. Pretty cool. Pretty cool. So do that again. Particle starting over here, and then it's going up. Awesome. Pretty cool. All right, let's do a couple more examples on the board. Ones where we actually need to, I guess ones that have sines and cosines, and where when we eliminate the parameter, we may need to use a Pythagorean identity. Okay, we'll see you back at the board. Okay, let's do some examples with sines and cosines, or ones where we have trig functions. So let's say the parametric equation, let's say x is controlled by sine squared of t, and let's say that y is equal to the cosine of t. Okay, let's plot the path that this particle here would be taking. Right, well, I think it's going to be, again, I want to think about the window that the path is going to live in, so I'm going to want to plot these here first. This one's going to be the easier one to do, or maybe one we're a little bit more familiar with. We know what the cosine function looks like. So the key thing to realize here is, well, what does cosine graph look like? It'll roughly look something like this. So no matter what t is, the y coordinate can only go between -1 and 1. So y is going to live between -1 and 1. So our path will only live in, I guess, this, -1 to 1 window vertically. Okay, what about sine squared of t? Okay, we don't have to plot this exactly. We just need to get a feel for it. So, okay, roughly speaking, what does sine of t look like? Okay, what does sine of t look like? Sine of t looks something like this, but we're not trying to look at sine of t. We're trying to look at sine squared of t. So what would sine squared of t look like? So I'm basically going to think about all these outputs here, but they're now going to be squared. Well, notice that the graph here, well, anything negative, when you square something negative, it's going to be positive. So no part of the graph will be below the y-axis. And also, when you square a number between, if you square a number like 1 squared is still 1. Okay, and what happens when you square a number between 0 and 1? Like, for example, what if you took 1/2 and squared it? Do you get something bigger? No, we actually get something smaller. 1/2 squared, 1/2 times a half is a fourth. 1/4 times a fourth is a 16th. So when you square numbers between 0 and 1, they get smaller. So what the graph of sine squared is going to look like, well, I'm going to get values between now 0 and 1, and it's probably going to look something like this. I mean, all these values here will just be squished down a little bit. Maybe I'll just graph them on top of one another. All these values will be squished down a little bit. They'll be a little bit smaller. Okay, but now what's going to happen is now these negative values, when you square them, they're now going to go from negative, they're now going to be positive. So sine squared is probably going to look more like something like this. Again, this is a rough sketch. So that's roughly what sine squared is going to look like. So now I've plotted sine squared in green. But the key thing we really just need to hold on to here is the window that the x values live in. So the x values will actually live between 0 and 1. So if we're thinking about the window our entire path is going to take on, it's going to have a window from 0 to 1, and then from -1 to 1. So we'll have this small portion. Okay, I'll graph it in just a second. Let's try to eliminate the parameter here. Now what's a little bit tricky is it's hard for me to plug one into the other. For these type of situations, remembering the Pythagorean identity sine squared plus cosine squared is equal to 1 will be very helpful for us. So recall that sine squared of t plus cosine squared of t is equal to 1. Well, sine squared is the same thing as x, so I can replace sine squared with x. This becomes an x plus, well, cosine of t is the same thing as y. I guess if you squared both sides, now cosine squared would be the same thing as y squared. So here we'll just get a y squared will be equal to 1. So here we've eliminated the parameter. Okay. Let's erase a little bit of this so we can have a little bit more room. Key thing we realized is that our x coordinates here, x can only go between 0 and 1. Here our y coordinates can go from -1 to 1. And when we eliminated the parameter, we got x plus y squared. So we got x plus y squared will be equal to 1. Okay, there's a couple ways we could think about plotting this. It might be easier for... Here, I'll give you two ways to think about this one. One way to think about it is you could solve for y. So you could say that y squared is equal to 1 minus x. Okay, and then you could say that y is equal to the plus or minus square root of 1 minus x. Okay, if you're thinking about function transformations, this you might be a little bit uncomfortable trying to reason what this graph is going to be. But 1 minus x is the same thing as negative x minus negative x plus 1. Let's go ahead and factor that negative out. So if I factor out the negative, this will be x minus 1 now. So this is going to be a square root function. I guess if we just think about the positive square root of negative x minus 1. So the square root function would normally look something like this. But what we've done here is we've subtracted 1 from the x coordinate, so that's going to shift the graph to the right 1 unit. But now I have this negative. When we have a negative on the input, that reflects it over the vertical axis. So we have a reflection over the vertical axis, and we're shifted right 1 unit. So this is going to look like the square root function, except now it's reflected over the vertical axis and it's shifted to the right 1 unit. Okay, that's what this graph here looks like. That's the positive version of it. The negative version, when we have a negative on the outside of the function, that reflects it over the, I guess, horizontal axis. So the negative version of it would be this lower portion. Okay, so this is the graph of x plus y squared equals 1. Okay, if you absolutely hated thinking about function transformations like that, I'm going to offer you a different way to think about it. Okay, instead of trying to solve for y, you could instead solve for x. You could say that x is equal to 1 minus y squared, or you could say that x is equal to, how about negative y squared plus 1? So this, I mean, usually maybe you're not super comfortable with having your x and y's flipped, but think about it like this. What if it was y equals negative x squared plus 1? If you were going to graph this, that would look like a frowny face parabola shifted up 1 unit. It would look something like this. Here's our y-axis and here's our x-axis. Okay, but what are we doing here? We're just flip-flopping the x and y-axis, or flip-flopping the variables. So if we want to graph x equals negative y squared plus 1, we are just going to flip the axes. We're replacing x and y. So it won't be a frowny face parabola. When I swap these axes, it is actually going to be a parabola that's going to be opening up to the left. So if we're plotting x equals negative y squared, I'm thinking about taking this and reflecting the axes. So let's plot that right here. Okay, so here's x, and here's y. If we want to plot x equals negative y squared, okay, it'll look something like this. Okay. This section's, if you haven't noticed, is very, very graphical. We gotta pull like we gotta remember all our toolkit functions. We gotta remember our transformations. We gotta remember what happens when we flip-flop x and y's. I can't really stress enough how important it is to know your toolkit functions, to know transformations, knowing what happens when you flip-flop your x's and y's. When you get to calculus, you're going to be needing to do this type of thing all the time. It's a great tool. Okay, that's why hopefully it's stressed so much in 141 and 99. Okay, but is this the entire region that our path is going to take? No, the x is only going to go from 0 to 1. So from 0 to 1, we're only going to have this portion of the graph. And while I didn't write it, this should be 1, and this here is negative 1. 1 and negative 1. Okay, so this is the portion, this is the path the particle is going to take. But how is it going to traverse it? Well, it's going to be bouncing back and forth. Sine squared. Remember that this graph sine squared kind of looked like this. And for y equals cosine, that looked something like this. So at time, sine squared. I graphed cosine squared here. Sine squared would look like this. Okay, well, at time t equals 0, the x coordinate is going to be 0 and the y coordinate is going to be 1. So at time t equals 0, we're at the coordinate 0, 1. Right? 0, 1. This is where the particle starts. At time t equals 0, if we're starting at time t equals 0. But as time goes on, what's going to be happening? Well, the x coordinate is going to get, looks like the x coordinate is going to get bigger. It's going to go towards 1, and then it's going to go back to 0. It's going to be bouncing between negative 1 and 0. So the x coordinate is going to be going back and forth between 0 and 1. And what's the y coordinate going to be doing? It's going to start at 1, and it's going to go down to 0. It's down to 0, and then the y coordinate is going to be negative. So the y values are bouncing between 1 and negative 1, and the x values are bouncing between 0 and 1. So as time goes on, the particle is going to do this, and then it's going to bounce back. So for this parametric equation, this is what the path is doing. It's bouncing back between these two spots. Pretty cool. Let's do another example where we're going to need to use Pythagorean identities to eliminate the parameter. So let's say that we have that x is controlled with 2 cosine of t, and that y is controlled with 3 sine of t. Okay. Well, if we're plotting x equals 2 cosine of t, get a rough sketch of this, the amplitude will be 2. Okay, and cosine starts at the top of the amplitude, so be doing something like this. Okay, so the x values are going to live between negative 2 and 2. Okay, y equals 3 sine of t. Okay, so this will have an amplitude of 3. So here's 3 and here's negative 3. Sine starts at equilibrium. It'll look something like this. Okay, so our y values are between negative 3 and 3. And it's good to note here that there's no restriction on time. Time can go from negative infinity to infinity. Okay, so what curve are we going to get here? Well, let's go ahead and write down the Pythagorean identity. Cosine squared of t plus sine squared of t is equal to 1. Okay, let's remember what this means. Cosine squared really means cosine of t quantity squared, and this will be sine of t quantity squared will be equal to 1. Okay, if we solve for cosine of t, if you divide both sides by 2, cosine of t will be the same thing as x divided by 2. So we'll replace cosine of t with x over 2, and we'll replace sine of t. Well, sine of t is the same thing as y divided by 3, so we'll do a y over 3 squared will be equal to 1. Well, if we distribute the square, this is the same thing as x squared over 4 plus y squared all over 9 will be equal to 1. So if you are familiar with your conics, this is the equation of an ellipse. This is the equation of an ellipse, which I think we saw an example of in I think the first Desmos animation from this video. Okay. Okay, a great way for me to think about an ellipse is, for example, if you were to kind of remove this divide by 2 and divide by 3, you just have x squared plus y squared is equal to 1. That's the equation of a circle of radius 1, the equation of the unit circle. Okay, but what are we doing? We're dividing the x-coordinate by 2 and we're dividing the y-coordinate by 3. Remember, with function transformations, when you divide x by 2, that stretches it in the x direction by a factor of 2. When you divide the y-coordinate by 3, this stretches it in the y-coordinate by a factor of 3. So this is like a unit circle, but we are stretching it in the x direction by a factor of 2 and stretching it in the y direction by a factor of 3. It's a great way to think about it. So let's sketch this ellipse real quick. Okay, so 2, negative 2, 3, negative 3. Okay, so here's the ellipse. Okay, here's our ellipse. Not the prettiest ellipse. Let's do that just a little bit better. Let's do that just a little bit better. Here's our ellipse. Okay. Okay, so the particle is traveling around this ellipse. This should make sense. We're saying that x is between negative 2 and 2, and y is between negative 3 and 3. Well, what's the particle doing? Okay, how is it traveling? I want to know, is it traveling clockwise? I'm sorry, is it traveling counterclockwise, or is it traveling clockwise? Well, you could plot a few points, or you could plug in a couple values of t if you'd like, but just looking at these graphs, at time t equals 0, the x-coordinate is 2, the x-coordinate is 2, and the y-coordinate is 0. So at time t equals 0, we're here. Okay, now what's going to happen? Well, as time goes on, the x-coordinate is decreasing. At least in this, initially, the x-coordinate is going to be decreasing, and the y-coordinate is increasing. X will be decreasing, y will be increasing, so we must be traveling this way around the curve. Beautiful. And it's just going to keep going around the curve, in this case, counterclockwise. Something interesting to do here is, what if we actually swapped sine and cosine here? So what if we swapped sine and cosine? What if this was now sine? What if this was sine and this was cosine? What do you think? Do you think we're going to have the same path? Do you think we're going to have the same path? Do you think we're going to be traveling it the same way? Will the ellipse be oriented different? I don't know. Let's see. Okay. So now the x-coordinates, here's 2 and here's negative 2. Okay. Here's x and here's t. Okay, here's y and here's t. Here's 3 and here's negative 3. So something like this. All right. So we'll still have that x will be between negative 2 and 2. And we'll still have that y will be between negative 3 and 3. Okay, and if we want to use the Pythagorean identity, we'll do, how about sine squared plus cosine squared is equal to 1. Okay, well, sine is the same as x over 2. And cosine is the same as y over 3. Okay, so I think we're going to get the same exact ellipse. We're going to get the same exact ellipse. Interesting. So here's 3, Here's -3, here's -2, here's 2. We still have the same ellipse, but now how are we traveling along the curve? Okay, well at time t equals 0, the x-coordinate is 0, and at time t equals 0, the y-coordinate is 3. So at time t equals 0, we're at coordinates 0, 3, we're right here on the curve. Now in this case, as time goes on, what's going to be happening? Well, notice that the x-coordinate is now going to be increasing initially, and then the y-coordinate is going to be decreasing. The x-coordinate is going to be increasing, the y-coordinate is going to be decreasing. In this case, actually when I flipped sine and cosine here, we still got the same ellipse, except now we're actually traveling. Clockwise around the circle. Pretty cool. Let's go ahead and take a look at Desmos and animate these. We'll see you there. Okay, let's take a look at those last couple examples in Desmos. Okay, the ones where we needed to use the Pythagorean identity. I think the very first one we had was x was controlled by sine squared of t, and y was controlled with cosine of t. Okay. Start at 0. It's already plotting more than I wanted to. But I think when we eliminated this parameter, we ended up getting the equation x equals 1 minus y squared. So that's that sideways parabola that we sketched. Okay. And sine squared, let's take a look at that sine squared graph. So it's kind of roughly what I drew up on the board. So notice that the x values will only go between 0 and 1, between 0 and 1. And the y values will only range between -1 and 1. Okay. And so when we hit play, let's get rid of this. Keep those on here. When we hit play, let's start it at 0. That's exactly what we're getting. We end up getting the particle bouncing back and forth between these two spots. Pretty cool. Pretty cool. Okay, and notice, it's this part. It's only this portion of the parabola because we had those domain restrictions on the x's and the y's. The reason it's kind of stopping to graph there for a second is because over here for t I have it from 0 to n. So when I'm here at a negative t, it's not plotting this green. Seeing how it's an error. Well, if I put -10 here, and then went all the way back, and then hit play, then it'll trace it out. Cool. All right, let's take a look at the ellipse examples. So we had. Let's start at 0. Okay. So what did we have? The first one we did, we had our x was controlled with 2 cosine of t, and we had our y being controlled with 3 sine of t. 3 sine of t. Okay. And when we eliminated the parameter, we ended up getting x squared divided by 4 plus y squared divided by 9 be equal to 1. So we had that ellipse we drew up on the board. Okay, let's make sure this all works. So here's our x-coordinate. X-coordinate goes between -2 and 2. Our y-coordinate goes between -3 and 3. Let's hit play. And notice for the first example, when t was equal to 0, so it's plotting it from t from 0 to n, so it's plotting t from 0 to n, but n is 0, so from 0 to 0. We started right here. We started at the coordinate 2, 0, which should make sense. When t is 0, our x-coordinate is 2. When t is 0, our y-coordinate is 0, so that's why we're starting right here. And if we hit play, we can see that we are traveling along this ellipse. Looks like counterclockwise. Okay, let's go back. And then what did we do? Then we thought about what happens if we just swapped sines and cosines. So here we have sine. Let's actually pause on this one before I switch this to cosine. What do you think it's going to plot when I have 2 sine of t and 3 sine of t? Maybe think about that for a second. Okay, well, let's hit play. Well, it's going to be this line segment right here. We're kind of bouncing back and forth. Okay, can you think about why? All right, well, it should still make sense since our x component is 2 sine of t, that our x component can only go between -2 and 2, and our y component can go between -3 and 3. So it makes sense that the graph would live in this window, but notice here this would be x would be equal to 2 sine of t. So if you solve for sine of t would be x over 2. If you replace this sine of t with x over 2, you'd have y would be equal to 3 times x over 2, or you'd have y would be equal to 3 halves x. That's a line with slope 3 halves. And notice here, this is a line of slope 3 halves. You know, you run 2, you rise 3, or a rise is 3, or run is 2. So that's why we're getting this line segment, but we're only bouncing back and forth between those two values. Fun. Okay, well, what if so we replaced x with sine, and then we had this one was cosine. And I think we just saw that the orientation for this case we still got that same ellipse, except now we were traveling, I think, clockwise rather than counterclockwise. And let's see that. If we push play, beautiful. Got the same shape, but for this one, now we are just traveling the other direction. Pretty interesting, pretty cool. All right, well, that's all I have to talk about for parametric equations. You go in much deeper depth into parametric equations. You actually end up doing them, and not in 2 dimensions, but in 3 dimensions when you get to calculus 3. And that would be, I guess, more realistic. We live in a 3-dimensional world. Every particle has an x, y, and z component, and then as time moves on, your x, y, and z component changes. So if you are going on to calculus 3, you will be able to use parametric equations to model something moving in what I would call real space. And you actually can think that actually technically our world is 4-dimensional. You need 4 components to tell you how to get somewhere. You know, like think about if you have an interview for a job. You know, they have to tell you a location. So you have an x coordinate, a y coordinate, and a z coordinate. Maybe the z coordinate is the height. You know, x and y's would be like the roads. Maybe the road you would use to get there, and then the z would, maybe if you're in an elevator, you'd have to go up to a certain floor. But the other piece of information you need to know is time. So really you would need 4 pieces of information to get to a location. We really kind of do live in a 4-dimensional world. I don't know, kind of fun. So anyway, I guess I'll say it one more time, but I really enjoyed being your instructor this quarter, and I hope I get a chance to meet a lot of you in the future. Take care. We'll see you later. Bye-bye.